Hi everyone, hope all of you are fine and making proper use of your time. Today we are going to discuss the concept and formula of wave optics which are useful for solving the questions from your JEE, NEET and GUJCET exam. Okay, so let us start it quickly. In this chapter, we had studied regarding the wavefront. Okay, now you know that wavefront is a plane in which all the points are having same phase. What does it mean? If I am having a wavefront, then all the points which are lying on the same wavefront will have same phase. So I can say that all the points on a wavefront have same phase. Now you know different shapes of the wavefront, and the shape of the wavefront is according to the source. All of you know that if I am having a point source, then wavefront will be spherical. If I am having a line source, then wavefront will be cylindrical. And in the same way, if the waves making the wavefront are parallel, then the wavefront will be the plane wavefront. Okay? Then we also had discussed regarding Huygens principle, which is the very basic principle. According to this principle, all the points lying on the wavefront behave as secondary source, and all this secondary source emits secondary wavelets. Okay? So, here, suppose I am having a plane wavefront. Then, all the points which are lying on this wavefront will continuously emit secondary spherical wavelets. Okay? So, they will emit waves in all the direction. Okay. Then after some time, all this wave, I am considering this one. So here also. Okay. So after some time, if I draw a tangent to all this one, I will get another wave. So this is your wavelets. I am drawing tangent. So this tangent gives me position of the new wavefront after some time, as well as you can see this wavefront is a plane wavefront. So we can say that using the principle of Huygens, we can find position and the shape of the new wavefront. Remember that if original wavefront is spherical, new wavefront will also be spherical. Original wavefront is plane, new wavefront will also be plane. That means shape of the original wavefront and shape of the new wavefront remains same. So this is Huygens principle. Okay. Now one more thing, relation between velocity of the wave, frequency and the wavelength. So you have to remember this relation. Velocity is equals to frequency multiplied by wavelength. That means frequency and wavelength are inversely proportional. This is one more relation. This V is equals to omega by. Okay, now we have to discuss regarding Doppler effect. This Doppler effect you have studied in 11th standard also in chapter of waves. You might recall that whenever there is relative motion between the source and observer, relative motion, that means distance between source and observer is changing, then frequency experienced by the observer is different from the frequency emitted by the source. Okay, this effect is known as Doppler effect. Doppler effect is applicable for all type of wave, whether it is sound wave or it is light wave. Okay, so whenever there is a relative motion between the source and the observer, frequency experienced by the observer is different from the frequency emitted by the source. This is our Doppler effect. Okay. Now, in some cases, observer will experience frequency lower than the actual one, and in another cases, he will experience frequency greater than. How it is possible? Or what is the case? Right now we will discuss what is the case. How it is possible we already have discussed, and still if you want to know, you can ask me on the WhatsApp. Okay. So when the distance between source and observer is increasing, then frequency experienced by the observer is smaller than the frequency emitted by the source. And you know that frequency and wavelength, they are inversely proportional. So if frequency is lesser, then wavelength is more. So wavelength according to observer is greater than wavelength of the source. So this increase in wavelength is known as redshift. Remember this thing. This can be asked in GUJCET. Increase in wavelength is known as redshift. Okay. Similarly, second case, if distance between source and observer is decreasing. If the distance is decreasing, then frequency experienced by the observer is greater than the actual frequency emitted by the source, and hence wavelength according to observer is smaller compared to wavelength of the source. This decrease in wavelength is known as blue shift. Increase in wavelength red shift, decrease in wavelength is blue shift. Now how much decrease? So fractional change in frequency is delta nu by nu. Change in frequency divided by original frequency equal to minus V radial upon C. Right, now V radial, what is V radial? V radial is radial component of Vs. Vs means source, speed of the source in direction of the line joining observer and source. As for example, suppose here is the observer and here is the source. Suppose source is moving in this direction. Okay, so this is the direction of Vs. Okay. Now V radial is the component of Vs along the line joining O and S. So this is the line joining O and S. So I will get a component here. So this component is your V radial. Are you getting my point? V radial is component of Vs along the line joining O and S. V radial is positive when distance is increasing. You have to remember this thing. V radial is positive when distance is increasing. V radial is negative when distance is decreasing. Clear? So this is all regarding Doppler effect. You have to memorize this formula. Okay. Now this is for delta nu by nu. Now from this, if I want delta lambda by lambda, then what should be the case? Delta lambda upon lambda equal to, you know, these two, they are inversely proportional. So in case of delta lambda by lambda, we will not have this negative sign. So delta lambda by lambda is equal to minus delta nu by nu. Okay, that means it is equal to V radial upon C. So all this regarding Doppler effect. Now we will proceed for the next topic. Now let us discuss about interference. You know that interference is the phenomenon produced due to superposition of the waves. Okay, now all of you are familiar about the superposition, that's why we are not discussing it. Okay, now in interference there are two types of interference: constructive interference and destructive interference. We have to discuss about the conditions for constructive interference and destructive interference. You know that here we are having two sources S1 and S2. The two sources are separated by distance d, and the waves emitted from S1 and S2 superpose at point P on the screen. This one is the screen. Okay, so length of the path of first wave, that is distance between S1 and P, is R1, while path length of the second wave, that is S2P, is R2. So path difference is equal to, you can see R2 is greater compared to R1. So path difference can be written as R2 minus R1. So R2 minus R1 is path difference. Okay. Now from figure, you can see here, if I draw a perpendicular S1M, then this S2M is the additional path length for ray 2, because this distance from S1 to P and M to P, they are same. That means I can say that this ray 2 has to travel larger distance, that is S2m. And from this triangle S1, S2m, I can say that this S2m is nothing but d sine theta, because this angle is theta. So I can say that path difference can be written in form of R2 minus R1. It also can be written as d sine theta. So path difference, which is equals to R2 minus R1, is equals to d sine theta. This is equal to n lambda. So this is the condition for constructive interference. You know that for constructive interference, bright fringes will be produced. So this is the condition in terms of path difference. I can also obtain the condition in terms of phase difference also. Now, do you know what is the relation between path difference and phase difference? We have already discussed in the class. Can you recall? Yes. So, phase difference equal to 2 pi by lambda into path difference. Using this condition, you can obtain, using this formula, you can obtain the condition for constructive interference in terms of phase difference also. So, in terms of, phase difference is equal to 2 pi by lambda multiplied by path difference. So, if I multiply 2 pi by lambda and this path difference, then you will get n lambda multiplied by 2 pi by lambda. So you can obtain it by your own. Okay. So in this way we can obtain condition for constructive interference. Now we have to discuss regarding destructive interference. In destructive interference, dark fringes will be obtained. That means there will be no light. So condition for destructive interference is path difference is equals to 2n plus lambda into 2n plus 1 into lambda by 2. So I can say that means R2 minus R1, which is equal to d sine theta, equal to 2n plus 1 into lambda by 2. Here also n equal to 0, 1, 2, etc. Okay. Now, see, in case of constructive interference, if I put n equal to 0, I will get n 0 into lambda, that is 0, that means path difference is 0. And for n equal to 0, when path difference is 0, I will get central bright here. And exactly on perpendicular bisector of this S1 and S2, I will get central bright. Two waves will superpose here, path difference will be 0, central bright will be formed. If I put n equal to 1, I will get first bright. So, n equal to 0 represents central bright, n equal to 1 represents first bright, n equal to 2 represents second bright, and so on. Well, in case of destructive interference, if I put n equal to 0, what I will get? This is 0 plus 1, that is lambda by 2. So at distance lambda by 2, I will get first dark. Okay. So here you have to keep in mind that in case of destructive interference, n equal to 0 represents first dark. Be careful. N equal to 1 will represent second dark. N equal to 2 gives you third dark, and so on. So whenever you are considering destructive interference, suppose in question it is given that fourth dark, then you have to consider for fourth dark, you have to consider n equal to 3. Be careful. Okay. Well, in case of fourth bright, you have to consider n equal to 4. Be careful. Here you can commit mistake, that's why I am putting the stress. For constructive interference, whatever is the order of range, you have to take n equal to same value. But in case of destructive interference, whatever is the order, value of n will be 1 less compared to that. For fifth, you have to consider n equal to 4. Okay. So, this is regarding two types of interference, constructive and destructive. Okay. Now, we will proceed further. Now, let us discuss regarding intensity. Now, when two waves having each of them having intensity I0, they superpose at a point, then average intensity that point is given by I equal to 4I0 cos square phi by 2, where phi is the phase difference between two waves. Now, we know that maximum possible value of cos square is 1. So, when cos square becomes 1, average or maximum intensity I maximum will be equal to 4I0. Clear? So, I maximum, possible maximum intensity is 4 times the intensity of each wave. Okay? Here it is the case of two waves. Now, instead of two waves, when three waves superpose, so I can say that for three waves, when three waves superpose, each of them having intensity I0, then I maximum will be 9 times I0. For four waves, I maximum is equal to 16 times I0. Similarly, for n waves, n number of waves, each of them having intensity I0, maximum possible intensity I maximum equal to n square I0. You have to remember this formula. I maximum is equals to n square I0. Now let us recall the formula of distance between two consecutive bright or two consecutive dark fringes. You might be able to recall this formula. This beta is equals to lambda capital D upon small d. Lambda is wavelength, capital D means distance between source and screen, and D means distance between two slits. Okay. Now in case of interference fringes, you know that all the fringes are having, all bright fringes are having same intensity. Second thing, width of all the fringes are also same. Remember, this is for interference fringes. Okay. Now, shape of interference fringes. So, intensity, sorry, it will be straight line if capital D, that means distance between slit and the screen is very greater than fringe width, then the interference fringes will be of straight line. Otherwise, the interference fringes will be of in the shape of hyperbola. Okay. Now, one more point we have to just keep in mind that suppose these are the two slits S1 and S2. We are considering Young's double slit experiment. In Young's double slit experiment, you know that there is one source. Okay. From one source, the two sources are created. Try to recall the Young's double slit experiment. And here I have the script. Now, if my main source is on perpendicular bisector of S1 and S2, then central bright will be on, here will be the central bright, it is also on perpendicular bisector. But what will happen if this S is, or the main source is not at perpendicular bisector, but it is somewhere here. Suppose this is the new position of the main source. Suppose this makes an angle theta here. Then in this case, if my main source is shifted, central bright will also shift. So it will be at the same angle but on opposite side of the bisector. So here this will be O dash will be the new position of central bright. So keep in mind that if main source is on perpendicular bisector, central bright is also on perpendicular bisector. But if the main source is not on perpendicular bisector, then the central bright will also not on perpendicular bisector, but it will be shifted by same angle but on the opposite side. So this is the point you have to remember for conceptual questions. Now let us move towards the next topic, that is diffraction. You know that whenever some obstacle comes in path of the wave and the edges of the obstacle are sharp, then that wave will bend at the edge. This phenomenon of bending of the light wave is known as diffraction. So what is diffraction? It is bending of the wave. Now one more point you have to understand, that this diffraction is the effect produced due to limited part of the wavefront. You have to remember this statement. Now I will explain you what is it. What does it mean? Okay. See, when a light is passing, here we are considering the light in form of wavefront. So when a wavefront is passing, a small portion of the wavefront, suppose a slit is here, then a small portion of the wavefront will pass through that slit, and due to that this diffraction patterns are produced. So not the whole wavefront is producing the diffraction, but a small portion, that means limited part of the wavefront is producing wavefront. So we can say that diffraction is the effect produced due to limited part of wavefront. Okay. Now amount of diffraction. Keep this point in your mind. You have to memorize this. Amount of diffraction is dependent on lambda by d, ratio lambda by d. Lambda is the wavelength of the light and d is the width of the slit or width of the opening. And from this only we can say that amount of bending for light is less and amount of bending for sound wave is more. Because for sound waves, lambda by d, lambda is more, so lambda by d will be more, and for light waves, lambda is smaller, so lambda by d is smaller. So bending of sound wave is more compared to bending of the light wave, and this is the reason due to which we can hear the person who is outside the room, but we cannot see the person who is outside the room, because bending is not there. As bending of the light is not there, we cannot see the face of that person. Okay. Now the conditions. Okay. You know this thing, that in case of diffraction pattern also we will get maxima and minima. Maxima represent bright, minima represent dark. So we will just recall the conditions for maxima. Path difference means represented by d sin theta is equals to 2n plus 1 lambda by 2, while in case of minima it is n lambda. It is exactly opposite to that in case of interference. In case of interference, n lambda produces bright, here n lambda produces dark, and 2n plus 1 lambda by 2 produces bright. For central maximum, that is central bright, path difference, that is d sin theta equal to 0. It means that here theta will be 0. So central bright will be produced when theta equal to 0. So all this is the basic formula for diffraction. Now we will discuss about optical instrument, that is microscope and telescope. We have to discuss regarding their resolving power. Now all of you are familiar about the term resolving power. Resolving power means ability of the instrument to resolve two separate objects. That means ability of the instrument to show two images of two different objects. Okay. So now let us recall the formula for resolving power for microscope as well as telescope. Okay, now resolving power for telescope formula, simply you just remember the formula. Rp is equal to 1 upon delta theta is equals to d upon 1.22 lambda. Here delta theta is known as limit of resolution. Limit of resolution means the minimum angular separation at which two objects can be seen separately. That means suppose here are two stars, okay, and this is the objective lens of the telescope. So these two, they subtend angle delta theta. So minimum amount of the angle for which the two stars can be seen separately. This is known as limit of resolution. If the stars are nearer, then this angle will be smaller than delta theta. In that case, the two images cannot be created, only one image will be created, or we can say that the images has not been resolved. Okay, so delta theta is known as limit of resolution, and here it is d, that is diameter of the objective lens, lambda is the wavelength of light used. Okay. Now in case of microscope, resolving power is equals to 1 upon d minimum. Once again, d minimum is also known as limit of resolution, but in this case it is not the angular separation but the linear separation. Separation between two objects, linear separation between two objects for which the two images can be created. That is known as d minimum. It is equal to 2n sin beta upon 1.22 lambda. This n is the refractive index of the medium in which the objective lens is kept, and this total 2n sin beta is known as numerical aperture of the objective. 2n sin beta is known as numerical aperture of this objective lens of the microscope. So try to remember the formula. For telescope is d upon 1.22 lambda, while in case of microscope it is 2n sin beta upon 1.22 lambda. So this is resolving power. So in this way, topic of diffraction is also completed. Now we have to discuss about the polarization. This is the now let us start the next topic, that is last topic, which is polarization. Okay. Before discussing the polarization, we have to discuss about unpolarized light and polarized light. We know that light is also electromagnetic wave. That means it is consisting of electric field vectors and magnetic field vectors. Now in unpolarized light, in case of visible light, we have only E vectors. In case of unpolarized light, these E vectors are uniformly distributed in all the directions. That's why we symbolize it like this. This is the symbol for unpolarized light. All this represent E vectors. So you can see that E vectors, that means electric field vectors, are uniformly distributed in all the directions. While in case of polarized light, E vectors are along one direction only. All the E vectors are parallel to each other. So this is the symbol for polarized. Okay. So main difference, E vectors are uniformly distributed in all directions in case of unpolarized light. In polarized light, E vectors are in one direction only. And the process of converting unpolarized light into polarized light, from unpolarized to polarized, this process is known as polarization. So actually what we should do? We have to filter out all the components which are not parallel. The process of converting unpolarized light into polarized light is known as polarization, and the device which does this job is known as polarizer or Polaroid. So Polaroid or polarizer is the device which converts unpolarized light into polarized light. Okay. Now what is the polarizer? Once again, it is the device which converts unpolarized light into polarized light. Now, every polarizer has its own axis, which is known as optic axis. Now, suppose this is my unpolarized light. Here, I am keeping one polarizer. Let us say this is P1, and this dotted line represents its optic axis. So, what will happen? When this light passes through it, all the E vectors which are parallel to this optic axis, they can pass through it, and the E vectors which are perpendicular to this optic axis, they will be absorbed by this polarizer. So, I will have only the E vectors which are parallel to it. So, this is, so now all E vectors are in same direction. That means this is my polarized light, this was unpolarized light, it gets converted into polarized light. Okay, so all the E vectors which are parallel, they can pass through it. All the vectors which are perpendicular, they are absorbed by it. Then what about this type of vectors which are neither parallel nor perpendicular? In that case, those E vectors will be divided in two components. One component will be parallel to this axis, one component will be perpendicular. The parallel component will pass, perpendicular component will be absorbed. So in this way, this polarizer converts unpolarized light into polarized light. Okay. Now remember one thing. If intensity of this light incident on the polarizer is I0, then intensity of the light emerging out from this will be I0 by 2. That means 50% intensity will be emerged out. Okay. So remember that I emerging, okay, equal to I0 by 2. I0 is incident intensity, I is emerging intensity. So this is, you have to remember this one. Okay. Now you might be able to recall Malus law. Malus law says that I equal to I0 cos square theta. What does it mean? Suppose here I am having some polarized light. I allow this light to incident on a polarizer which has optic axis in this direction. Now you can see this is the light in this direction, this is the optic axis, this angle is theta. So I can say that intensity of light emerging out equal to I0 cos square theta. I0 is the intensity of light incident, I is the intensity of emerging light. So I equal to I0 cos square theta. Theta is the angle between E vectors and direction of optic axis. This is Malus law. Okay. Now let us discuss about Brewster's law. Suppose this is one medium, light incident on this medium in this direction. Consider this is the perpendicular. Now we know that some of the light will be refracted, some of the light will be reflected. Okay, this is reflected light, this one is refracted light, this is angle of incidence. Now this reflected light will be partially polarized. Okay, that means it is not perfectly polarized. Amount of E vectors which are parallel will depend on angle of incidence. So as angle of incidence changes, the amount of polarization will change. At particular angle IB, this reflected light will be perfectly polarized. The angle IB at which the light is perfectly polarized is known as Brewster's angle. Okay. And in this case, the reflected and refracted ray, they are perpendicular to each other. When angle of incidence equal to Brewster's angle, the reflected and refracted ray are perpendicular to each other, and in this case you have to remember Brewster's formula. N is equals to 10 IB. IB is Brewster's angle, N is refractive index of this material. Refractive index of the material N is equals to 10 of IB. Okay, so all this is regarding polarization. In this, all the concepts of chapter of wave optics. Now this is done for solving the question. So I will send you the question. All of you have to try to solve each and every question, and the questions that you are not able to solve, that we will discuss in our next session. So be active, don't waste your time, and stay safe and healthy. Okay, bye bye.